proof, and this is proof by contradiction. So this was newly added to the international A-level spec, and I think it's been taken away from the actual UK spec unless you do further. Okay? So proof by contradiction is where we're going to look at contradicting things. So there is a few steps that you need to do to in orderly gain successful marks. Number 1, state any information or assumptions you are using. Okay? So for example, if we use a negation statement, we also then need to, if you then use 2n, well, what is 2n? 2n is an even number. So if we're saying let k equal 2n, where 2n is an even number, we have to literally write everything down. That's the whole point of proof. Okay? Show every step of your proof clearly. Make sure it's logical and it follows from the previous step. Make sure you've covered all possible cases. So if you had to prove that 2 consecutive numbers add up to give you an odd number, you need to prove this for, not 2 consecutive numbers. If you were to prove that 2 numbers add to give you an odd number, you've got to prove, 2 numbers, you can either have odd, odd, even, even, odd, even, even, odd. These are only 4 possible cases, yeah? So you'd have to prove for all cases. Then write a statement of proof at the end of your work, and this is really important that we write that final statement. Okay, so we're going to make sure we go through this list on each question. Okay, so step 1, negation statements. All rich people are happy. How could we write a negation statement for this? All rich people are not happy. That is a negation. Perfect. If P and Q are prime numbers, then PQ plus 1 is a prime number. So what's the negation of this statement? Yeah, if P and Q are prime numbers, then PQ plus 1 is not a prime number. Okay, all numbers of the form 2 to the power of k minus 1 are either prime numbers or multiple of 3. So we're literally just going to put a not in there, aren't we? After the beginning of that statement. And that's what negation means. Okay, so we're going to prove by contradiction that there is no greatest odd integer. So step 1, what are we going to assume? So assume that there is a greatest odd integer. Okay, if we assume that there is a greatest odd integer, everyone happy with this first statement? Okay, so first of all, now I need to write down what is
2n plus 1.
2n plus 1. Okay, so we've now done our assumption. We now need to think, okay, what else are we going to do? So we know, so 2n plus 1 is odd. Okay? So 2n plus 1 is odd. What else do we know about this? We know that 2n is even. Is that going to help us right now?
2n plus 1 multiplied by infinity is still 2n plus 3.
2n plus 3. I kind of like where Faris is going, but we're not going to multiply by infinity. Why would we then write 2n plus 3? So we have to think what's happening here. So assume that there is a greatest odd integer. We've stated that 2n plus 1 is odd. Okay, let's go back to our steps. Okay, something else we need to do is odd and an integer. Yes or no? Yeah, because we're stating that it's an integer where n belongs to the real numbers, yeah? Okay? So 2n plus 1 is odd and an integer. So right, so shall we let 2n plus 1 equal the greatest odd number? Yeah? We now need to say what is the greatest odd number. We've said that 2n plus 1 is odd and an integer, but we can now say let 2n plus 1 be the greatest odd number. Okay, so we've now stated what number is. We've now stated it's still an integer. Now we're saying, let's let that be the greatest odd number. Okay, what is bigger than 2n plus 1?
2n plus 3. Consecutively this?
Just anything bigger. So then we could say this. 2n plus 3 is greater than 2n plus 1. Is this a fact or not?
Yes.
This is a fact, right? This is a fact that we've written down. Why is this true? This is true because this goes to, if we were like to take away 2n from both sides, we get 2n. 2 is greater than 1, yeah? So, we've now stated another fact. So we can write that down. So 2n plus 3 is greater than 2n plus 1. 2n plus 3 is also odd and an integer, is it not? Where n belongs to R. Therefore, there exists a greater odd. No, there is no greater odd. Therefore, so we're assuming that there is, therefore there exists a greater odd integer, like than we said, or maybe I'll change that. No, okay, let's put the normal word in. Therefore, this contradicts our assumption of greatest odd integer. Okay, so we've now said that there's a contradiction. Therefore, now with the therefore bit, instead of just writing therefore proved, okay, you're not going to get full marks for therefore proved. I want you to rephrase what was said in the sentence. So therefore, there is no greatest integer. Yeah? So therefore, there is no greatest odd integer, therefore proved. You can do that after if you want. Okay, so there we have it. Now, if anyone's following the textbook, they have a different proof where they use n. However, personally, I think when we're talking about odd numbers, we should be using 2n plus 1.
Miss, why do you put that there?
I put 3 dots in therefore. Yeah, these mean the same. Sorry, do you know, I was just a bit panicked, so I had to write a sentence. Okay, so next up. Right, so for this type of proof, proof by contradiction, if n squared is even, then n must be even. Okay, so what is our assumption going to be?
N squared is even.
So assume that if n squared is even, then n must be odd. Okay. So, if n is odd, okay, let's start with that. So, if n is odd, let n equal, what's an odd number? Let's use a different letter. 2k plus 1. Okay. Therefore, 2k plus 1 squared must be even, because that's what we're saying, right? So let's expand the bracket. So 2k plus 1 squared equals 4k squared plus 4k plus 1, right? 4k squared plus 4k plus 1, we know we can write as 2 lots of 2k squared plus 2k plus 1. What do we know about this number? It's odd. Okay? So this, and we could even say 2n plus 1 is an odd number. Now, can you see how I'm literally writing everything down, right? So then, therefore, this contradicts our assumption. Okay. And then you're going to write, therefore, if n squared is even, then n must be even. Therefore, proved. Prove by contradiction that root 2 is an irrational number. So what's our assumption going to be? Yes, we're going to assume root 2 is a rational number. Okay, now, what is a rational number? A over B is a rational number where A and B do not share any common factors, okay? Okay, so if root 2 is rational, that means root 2 could be represented as A over B, okay? Where A and B are two different integers with no common factors.
This rational number is just integers.
Okay? Because what we're saying now is we're saying let this be a fraction where, for example, we wouldn't want it to be this fraction. For example, 4 over 10. If it was 4 over 10, that would mean that they both share a common factor of 2. So, for example, we want to say that A and B have no common factors. For example, what I'm trying to say is A and B actually look like 2 over 5. Okay? Yeah? Does anybody know what that makes A and B if they have no common factors?
Rational. Oh, no.
So, no, a rational number is something that can be written as a fraction. For example, if you put root 2 into your calculator, it'd give you 1.41, blah, 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 blah. It will never be a fraction. Okay?
So rational numbers are integers? Is that true?
Well, no, rationals are not integers. What's 2 over 5 is 0.4. Is that an integer?
So 2
Yeah,
over
but
5
that's
is
not-
irrational.
They don't have the common factor.
Rational, 2 over 5 is a rational number. Why? Because it can be represented as a fraction.
Anything that is written as a fraction is irrational.
Yeah, for example, 1 over 3 is rational.
So you're saying 2 over 4 is irrational?
No, 2 over 4 is still rational.
Or 2 over 2 is irrational?
2 over 2 is a whole one,
Yeah, so that's irrational.
which is an integer. It can still be represented as a fraction, 2 over 2, so it's still rational. Irrational means no matter what you do, you can never represent it as a fraction. Could you represent pi as a fraction?
That's why.
No, so it's an irrational number.
That's why you
Yeah?
click the SD button and get root 2. I told you this.
Yeah, so if you put root 2, you know, like sometimes we put things in our calculator and then you press SD to get the decimal because it gives you a fraction first. Numbers that go straight from the calculator to the decimal, they're irrational.
So it's only root numbers that can be irrational,
No, loads of different numbers can be irrational.
such as
Pi, E. Okay, right, so let's see where we go from here. So where A and B are two different integers with no common factor. So let's square both sides, right? Because right now I've stated everything. I have no idea where I need to go with this, but I do have an equation here which says root 2 equals A over B. Is this true or false? True. So technically I could square both sides, right? Because I can manipulate what I have. Is squaring both sides okay?
yes.
Absolutely. So this therefore means that 2 equals a squared over b squared. Right. So technically, could I multiply both sides by b squared? Yeah, of course I can. Right. So that means 2b squared equals a squared. Yeah? So what does a equal?
Even odd thing.
So therefore, then, that also means that root 2b squared equals a. So technically, root 2b equals a. So technically, I hate this proof. Technically, we could substitute it back in, couldn't we? Okay, but then we realise that, let's say we substitute this back in, okay? We go off on a side note. We substitute this back in. Instead of writing a, we write root 2b over b. They're going to cancel, so then we just get root 2 is root 2, right? So this is where you know then you've gone the wrong way. Okay? But what we have just realised is something even better. Okay? So just, by the way, this part is because people, when they do this in the exam, they get to this part and they get a bit...
You have to prove that.
what's it called?
Scared.
No, they don't get scared. They get caught in a loop. Okay, we actually have to come from here. Right, 2b squared equals a squared. But what if we actually said about a and b?
The square number cannot equal an even.
And what have we said about a and b? We've said that they have no common factors. We're practically saying here, what?
They're different.
That one is a multiple of 2.
Yes.
Okay, so from this bit, we now have to look at, we've said that a and b are 2 numbers with no common factors. We now need to look at, actually, what happens. You know when we said look at every possibility? So now we have to go with even or odds. Okay, so now we have to say, right, so let's assume from here what? That a is even? Yeah? So, let a be even. Okay, and this is because a squared equals 2b squared. So a squared equals like 2 lots of something, right? So then a is definitely even. Right, if a is even, what do we know about a?
If A is even, that means
If a is even, that means we can represent a as 2n. So a equals 2n, okay? Because we're saying that a is even. What does n equal? What we're saying there, we're saying that n is an integer, right? So where n is an integer. Okay. So now that we have that, what do we know?
The b has to be odd.
So we know that 2n squared has to equal 2b squared. Yeah? So then we're going to have 4n squared has to equal 2b squared. Okay? What does that mean? That means that n squared, 2n squared has to equal b squared. Okay?
Oh, you can divide by 2. Yeah.
So what does that mean? Well, that means that b squared is also even. Does it not?
Yeah.
Yeah? So b squared is also even. Therefore, b is also even. Okay? Yes. What do we know? So if A and B are both even, yeah, they share a common factor of 2. Okay, does that contradict our statement?
Yes.
So this contradicts our assumption. Therefore, root 2 is a rational number. Irrational number. I think I've spelled rational wrong. It doesn't matter. Perfect. So, with these types of questions, I've also seen saying assume that root 3 is an irrational number, and then you've got to use that. Just make sure, just keep going and just say, okay, well, once you get to here, and you know that this is even, then start substituting. You know what even is, you know what odd is, okay? Start going with that, and it's a case of you're trying to prove that you're wrong, so look for loopholes. Okay, so we need to prove by contradiction that there are infinitely many prime numbers. So what we're going to assume? We're going to assume, yeah, there is a finite. Assume there is a finite number of prime numbers. Okay? So, that means that we could actually write a list of all the prime numbers that exist, yeah? So, therefore, prime numbers that exist is P1, P2, P3, all the way up to Pn. Okay? So, are we ready? So now we're going to consider. Sometimes when you don't know what to write, just write consider. You know in the first one earlier where we did the 2n plus 3 is greater than 2n plus 1, we could have actually then written consider 2n plus 3 is greater than 2n plus 1, because this is true, right? Right, so now let's consider a number where we have P1, P2, P3, etc. And, we're going to multiply them together, okay, and the last one, and add 1. So we'll multiply all the numbers together and then add 1. So this number that we've considered is one more than the product of all the previous prime numbers. Okay? So, when we divide n by any of the prime numbers, P1, P2, P3, we're always going to get a remainder of 1. Okay? So, we've considered n because, for example, if we did n divided by P1, we would end up with a product of prime numbers. So this one would be like P2 to Pn. But the whole point is that we're going to have a remainder of 1. Okay? We're always going to have a remainder of 1. So this means, okay, so n divided by P1 is going to give me a remainder of 1. So n divided by any P gives a remainder of 1. Okay? So this is true for all accounts. No matter what we do, if we were to divide it all by P2, what we'd have the product plus 1. Now the whole point of having this remainder is because we know that with prime numbers, they can only be divided by exactly 1 in itself. So if we've got a remainder, this is good news, right? Because this means it's not entirely divisible without having a remainder. So we're saying if we're dividing it by anything but that number, we are going to have a remainder. We're just proving right now that this remainder is 1. Okay? So that means, that no numbers, so no prime numbers, that exist, you know, in our list earlier, P1, P2, P3, ... Pn, are factors of n. What do we know about prime numbers? They have exactly 2 factors. So we're now saying that no prime numbers are factors of n. Well, this is good because we don't have to worry about even or odd. If a prime factor isn't even a factor, this is a good start into making sure that we know what is a prime number. Okay? So, what does that mean? This means that therefore n must be prime, or, okay, now this is a bit cheeky, n must be a prime number, okay, or have a prime factor which isn't on our list. Or have a prime factor which is not on our list. Okay, but what did we say about our list? We said that in our list there exists a finite amount, and we already have done the finite amount. So what is it? Therefore, contradicts our assumption. Therefore, there are infinitely many prime numbers. Okay? Therefore proves. So what we're trying to show here is that we know that a prime number has exactly 2 factors, one in itself. We're trying to show that there is a number that is made up of prime numbers, so that when we are looking at the factors, we're saying we have 1 remainder. Okay? This is what's happening here. Okay, so thank you for watching. I'll do some exam questions as well. These are just a few of the typical ones. Have a great day.